Hi everyone, it's Anirudh from 61B, and today we're going to be talking about the Spring 2022 final exam, specifically question number 8, which has to do with 2-4 LLRB trees. So I like this problem. I'm a little biased because I'm the one that suggested it, but I think it's pretty cool because we're sort of thinking about applications of breadth-first traversals and how that affects how we might ideally want a B tree to work versus how our representation as an LLRB makes it a little different and how we can account for that in part C with our code. Okay. Let's go ahead and start with part A. We have a given 2-4 tree, and we want to know the sequence of keys encountered in the breadth-first traversal. So in breadth-first traversal, right, we're told we're going to be going layer by layer and from left to right. So we start out with layer, like if you want like zero index, right, like our sort of like our root layer, or like our first layer, right, where we're going left to right. So we're going to go ahead and go left to right like that. Then we go to the next layer. We start at the left. So we're going to go block by block, and then in each section, right, in each group of these nodes, we're going to go ahead and print out them, right? So this would be, I believe, option D, and I'll go ahead and draw out the arrows underneath to correspond with the arrows that I drew above. Okay, so that's part A. Let's talk about part B. Now we want to do a LLRB corresponding to the 2-4 tree in part A, and then we're going to match it up with this diagram here and indicate what nodes are red, as if they are red, and then also indicating what values are there. Okay. So I'm actually going to go ahead and represent this up here in the upper right corner, and then I'll go ahead and duplicate it later just for ease of drawing. So remember that the kind of the point behind the LLRB is that we want to have a one-to-one mapping, right? So I'm going to go ahead and write that over here, right? So one-to-one mapping. So what does that mean? So if we have a choice, red on the left. Right, remember that we never have sequences of red layers, right? We always use like black and then red, and then it has to be black, right? But what this idea is saying is that, for example, if I look at this very top node 2-4, if I have 4 here, and then I could have 2 onto its left, and this would be one way to implement this, right? This would actually be the only way to implement this particular block in an LLRB. But another way that I could do this would be to have the 4, oh no, sorry, it wouldn't be red. Oh, sorry, it would not be black, it would be red. Let me go ahead and rewrite this. So I could have 2 up here, and then I could make 4 the red node, right? But we notice that the problem with this is if we have 2 different ways to do it, then we start breaking this idea of a one-to-one mapping, right? So it means that if I give any 2-4 tree, I should be able to extract one particular red-black tree. If I give you any one red-black tree, I should be able to extract one particular 2-4 tree. So we want to maintain that, right? Because it makes our life a lot easier and we think about how we're representing things. So we always want to bias toward the left one. But the reason why I bring this up is because if we have a case where we have multiple, right? So let's go ahead and erase this. And let me talk about a different example. So let's say we're doing like something like 5, 6, 10, right? Or even more generally, if I just have one black node, in a 2-4 tree, I can have up to 2 red nodes. And in this particular case, notice that even though this red node right here is technically on the right, right? It sounds a little weird because this is like still a left-leaning tree, because the idea is that we still have a one-to-one mapping, right? If I tell you that I have 1 black node and then 2 children red nodes, and it's a binary tree, this is the only representation that can work, right? In fact, if I was in like 5, 6, and 10, you know that 6 has to be up there, and then 5, I guess I can zoom in, 5 has to be right here, and 10 has to be right there. There is no other alternate mapping, right? So we don't have to worry about it being on the left. So that was just a quick idea of what we're doing, right? So now we can actually go ahead and start implementing this. So let's go ahead and start with that first layer, right? So we have 4 up here, and then we have 2 right below it. I'm going to go ahead and connect these 2. So that represents our first layer. And then we're going to introduce the next block, right? -1, 1. So I'm going to go ahead and add in 1 over here, connect it, and then we're going to have to add in -1 down there. And then we're going to add in 3. So 3 is just on its own, right? So we're going to just go ahead and add it in to the right of 2. And then finally, we get to the 5, 6, 10 block. And so in this particular case, right, we're going to have 6 with 2 children red nodes. This is the example that I just mentioned earlier, right? So it'll be 5 over here, 10 over here, and then I'll go ahead and draw on the links. It's not a perfectly drawn tree, but I feel like it's pretty close to, you know, like the computer representation. So I'm going to do now is I'm going to go ahead and take this. Let me just move it down a little bit. All the way over here. And I think that now right, we can pretty quickly match it up, right, with what we have given to us throughout like the letter options, right? So if I start out with A, we can see that it's 4. If I go to B, we can see that it's a 2, but it happens to be red. If I go to C, I can see that it is 6. D is 1, then E is 3, is 5, G is 10, with the 5 and 10s being red. And then we have a final -1 that is also red. Yeah, so that goes ahead and wraps up part B. And what's interesting here is that if I do the breadth first traversal, or at least what C is telling us, right, is that if I do the breadth first traversal from part A, right, so I look at the result 2, 4, -1, 1, 3, 5, 6, 10. That's what we want. So let me actually go and write that over here. So we want 2, 4, -1, 1, 3, and then 5, 6, 10. But what do we get? We are getting, right, so if I don't worry about this as like a red node, a black node, I just do a standard breadth first traversal, but we're gonna get something different. We're gonna get 4, 2, 6, 1, 3, 5, 10, -1, right? Which, you know, it looks pretty different to me, right? I think it's like, it's a little tricky to pinpoint, right, exactly how like the mapping works. But I think it's a little better to think about this in terms of layers, right? And I think that's really the insight of this question is, before we even look at the code, let's think about why that's the case, right? I think that that's going to give us some intuition for when we're looking at the code for why things are structured the way they are. So sort of like the idea, right, of what's going wrong is that we're not giving priority to the red nodes when needed, right? So to further illustrate what I'm saying, right? So let's consider like just this first 2 layers, right? So let me zoom in for a moment. So what we're doing in breadth first search, right, is we're going layer by layer. And so we're treating 4 as the first layer, right? So then we're printing out 4. But we've already gone wrong. Why have we gone wrong? It's because we're supposed to start with the 2, right? So if I represent this as the B tree, remember that this is 2, 4 at the very top, and then I have my 3 things coming out, right? And so if I want to do a BFS, right, treating this as a B tree, I should start with the 2, but it turns out that I'm starting with the 4 if I just think about this in the abstract. So what I should actually do, right, is I need to figure out some way to account for the fact that there's a red node, right? Because if there is a red node to the left of an item, that means that it's on the same layer as the item, and I need to print it before the item, right? And we can extend this reasoning, right? Because this is a 2, 4 tree and not a 2, 3 tree. So what's going on in this situation over here with the 5, 6, 10, right? So let's say that, for example, I account for it somehow, right? Like the 2, 4 issue. Well, the problem is that for 5, 6, 10, it should not be that 5 comes before 6, right? And then I treat 10 as its own thing. 10 should come immediately after, right? I should not print 5, then 6, and then go to 1, and then 3, and then to 10, right? Like in other words, I should not be going 6, right? Realizing there's a 5, printing it, and then coming down here. I have to complete the idea of accounting for all these red nodes. So what I can do is I can generalize this, right? By saying for some node, for some black node n, check its children to see if they are red, right? So that's sort of like the idea of what we're doing here, right? Is we want to be able to figure out some way of accounting for that. And then when we do account for it, we want to sequence it, right? So if I have 2 here, I want to put it first. If I want to have 10 here, I want to put it right after. So that's sort of the intuition that we have when we go into part C. So let's go ahead and take a look at what part C says. So we're given some class RB node, right? Red block node that has an integer key. It has 2 pointers, right, for the left and the right. Then it has some Boolean that marks whether or not it is red. Okay. So we're trying to print the keys in the same order as for the 2, 4 tree corresponding to the tree. So I'm going to go ahead with the assumption that you've already taken a look at the code, but I want to make a couple observations. So first off is that we can sort of think about this as a modified BFS, right? So if you think about how BFS works, right? Basically, we go into some node, we pop it off, like, or like I guess like when you pop the node off the queue, right? You're maintaining a queue of all these nodes. You pop a queue item off the queue, and then you add basically, you visit it, you do whatever you want to the node, and then you process all of its neighbors, and you add all those neighbors in order to the queue, right? Remember that queue, we're adding to the back of the data structure. And then we're going to repeat this process over and over until there's no more things left to remove in the queue. But the problem with that is, right, is that we want to account for this whole idea of the red node and then sequence things in the queue a little bit differently so that we get the right order when we print stuff out. So when we start out, right, we're initializing some queue and we want a queue add and then we have a while, right? So again, it's going to be pretty similar to the idea of a regular BFS. So we are going to go ahead and add in, right, our starting point, right? So we have to initialize our queue somehow, right? And so the way that we do that is we're given some parameter tree and we're going to go ahead and do queue.add on tree, right? So this gives us our first node to sort of start out, right? So if I go ahead and think about this right here is tree. In fact, to make things easier, go ahead and remove this. I'm going to duplicate this once more for reference. I guess not duplicate once more because I didn't duplicate the first time, I just moved it. But I guess I'll just keep it over here for now. Erase. Oh, I didn't mean to erase that. I meant just to erase the little dot. Okay, there we go. All right, so we have queue.add tree, where tree is up here. Right, so it's a pointer to this 4. Okay. Now we have some while, right? So it's going to be like the same idea as the BFS, right? All we're doing is we're accounting for the idea of the red node, but we're just accounting for the sequencing within the queue, right? That's what we want to account for. So we're actually going to keep like basically the exact same condition, right? So while the queue is not empty, and the way that we will represent that, right, is while not queue dot is empty, right? Remember that we are implementing this queue as a linked list, so we have access to the linked list methods. So that's why we're calling is empty. Yeah, okay. So then we have some node where we remove that first node. And then now things get a little interesting. We have an if statement, and then we have nested within that an if else, a regular print statement, and then an if else, right? And so going back to the idea, right, this is a modified BFS where we're accounting for the idea of a node being read somehow, right? If children nodes are being read. I think that's pretty good intuition for what we're trying to do here, right? I think especially when you consider the fact that line 14 and line 22 have print line statements, it means that we are sort of effectively accounting for visiting something a little bit earlier, right? So if we think about what our like what we're doing at line 20, right? We can sort of think about this as like this whole section, right, up here as being the left, this as being the node, and then this as being the right. Right, this is how like we can sort of think about like accounting for each of the children, and then we have these if else, right, statements as being accounting for whether or not a node is read, and then we're going to be able to adjust from there. I think that this part is like really like the jump that's like needed to like really like get this question. I think that like what I think will like make the most sense is if you think about this in terms of like what we're trying to do in the breadth first search, right, is that we're trying to sort of somehow process everything like on like we're going layer by layer, right? So we generally want to like go like through the entire layer, and then we go to the left, right, when we're adding to the queue. So for example, like if I had like this is not like a valid binary search tree, right, because 2 is to the like left, but if we're just doing a breadth first search through some tree, right, and I have like this, the idea is that I go here, and then when I add, so like I start with 1 in the queue, right, then I visit 1, and then I'm going to go ahead and add 2 and 3 in that order. When I visit 2, I'm actually going to go ahead and add 4 and 5, right? So I visit its left and right children, right? So we're generalizing that idea into this modified BFS. Go ahead, move that. So that's sort of like how we can sort of think about the structure of the code. And then we have this other if statement up on line 12, right? And I think that this one we can sort of think about as being like an edge case handler, right? So one thing that we can think about is what happens, right, if, for example, that I'm trying to access the left node of a child, right? Because remember that we're checking properties, right? What happens if I'm trying to access the left node or like the value added node where the node does not exist, right, for some reason? So then what we want to do is we want to go ahead and have a quick nullity check, right, to make sure that our node is not null, right? And remember that this can happen, right? Because what we're doing is we're not actually using any if statements within like any of the other lines to check whether or not a child is null, right? So when I'm doing like some queue add operations to add in like the left children, I'm not making sure, oh, is that left child like null, right? Instead, what I'm doing is I'll just go ahead and add it to the queue, but then the queue will just skip over all the null elements and that will take care of it anyway. Okay, so I'm actually going to start with line 20, right? So if I'm processing the node and I want to print what it is, all I have to do is just access node.key. Okay. right? So the idea is that if I'm at like 4, for example, and I want to print 4, I just print 4. Now let's talk about how I'm going to account for the 2 coming first, right? So if you notice, I think like sort of the key here is that we have the system.out.println statement, right? Which means that we're sort of visiting the item before. And then we also have 2 q.dot statements, right? So like we're doing 2 q operations and not just 1. So I think this is particularly useful, right? Because if you think about it, if I'm visiting 2, right? So if I think about this in terms of layers, I think about this as like the first layer. And then I'm going to go ahead and add, let's say I do in green, this as a second layer. Well, what I'm trying to do is I'm trying to access 2 first, but that's not enough, right? Because if I just do 2 and then I keep moving on like things don't matter, well, when is 1 and 3 ever going to be added to the queue, right? I have to add those to the queue as I visit something. That's sort of like the idea behind the BFS, right? So it's not enough for me to just print out 2, right? So if I like print 2 here, I need to add 1 and add 3, right? And otherwise, well, if I'm not going to print 2, I'm not going to add 1 and add 3. Well, I want to print 4 first, right? I want line 20 to print 4. If 2, for example, was not a red node, well, then I want it to be printed. So then what I can do is I can just skip over that and just add it for later, right? I can sort of sequence it at the back of the queue. So instead, I would just add 2, right? If it was not a red node, like it was just a regular black node for some reason, I would just go ahead and add in 2 directly. So for example, I think a better example, right, would be like if I've processed the 2-4 section and I look at this part right here, and let's pretend like -1 did not exist. Well, in that case, you wouldn't want to print out the 1 very quickly, right? You'd want to actually add it to the end of the queue, right? Because it's not like you're trying to sequence it in the same layer, it's in the next layer, and so you want to worry about it then. Okay, so, or actually, I'll keep that, I guess. It's not like exactly correct. It's correct, I guess, for like one particular part of it. But yeah, so like the idea is that we want to system out println on 2. But remember that at this moment, node is still referring to 4. So we need to access the node.left properties, right? So what I need to do is I need to print out node.left.key. And then if I'm going to add 1, add 3, I want to access, right, those. So I need to do node.left.left and node.left.right. Else I can just add, or actually I forgot to add something. Let me go ahead and move these over. Forgot to add in the add keyword, right? So we want to add to the queue. My bad, I just assumed it was there. Okay, so that's sort of the idea of what we're trying to do here, right? Is we're trying to add the left child of this left node, the right child of this right node, right? Given that it's a red. So I'll go actually and mark that here, right? So this if statement is checks left redness. Okay, and then at the bottom right, so we have that like that else statement, right? Where if it's not red, what do? We just treat it like normal, in which case we'll just q.add on node.left. Okay. Now let's talk about the if statement. And I think the reason why I actually wrote this stuff out first is because it's going to help us with the if statement on what we want to check, right? So I think, so like the very first thing that we might think of, right, is we just want to check left redness. So check node.left.is red, right? It'll give us a Boolean and then we can just go from there. But there's a slight problem with this, right? And the issue is that we're making a lot of access to node.left, but we're not even checking if node.left exists. Right, so an example is, let's say the node is 3. Let's say node points right here. If I do node.left, I'm going to get null because there is nothing from it, right? And then if I call .isRed on that, well, then I'm going to get an error, right? Because I'm trying to access a property of a null object, right? So what I need to do is I need to make sure that node.left is non-null, and then that's totally fine because remember that if node.left is null and then I add it, well, it'll just be skipped because of the way that we set up the line 12, right? That's sort of like our way to sort of like account for like nodes that don't have any more children. So really what I want to do is I also want to include that, and notice that I include that before, right? Because otherwise the actual if condition itself, right, will error if node.left is not null, right? So that's what I need to check first. So that's sort of like the pseudocode, right, for how node.left works. And it's actually a very, very similar process, if not almost the exact same for the right? Like the idea is that just like how we were talking about the 2-4, if I talk about like what happens with like a 5-6-10, right? So this whole like left redness, right? If we think about what would happen, we realize, oh, we're at 6. So let's say, for example, that we make it all the way to 6, right? Node points here. So what does our queue look like? Well, our queue at this point, right? Remember that we had 4 starting as our node. And then we checked its left. It was not null, right? Because we had a 2 item. it was red. So we printed out that. So we printed out 2. We added its children left and right, right? So the queue started out as being 4, right? But then we popped it. So then it became node. And then we're going to go ahead and add node.left.left, which is 1, node.left.right, which is 3, right? In that first part of the if statement. We print out 4, right? Because of the current item. And then we're going to go ahead and check the right. Well, the right, well, 6 is just a regular node. And so I know that it needs to be the next layer, not the current layer. I'm just going to leave that as is, right? And then if you notice, well, things just happen to work out because it means that if I have 6 in the next layer, well, then I would have added it to the queue, right? Because I would have triggered this else statement, right? In the if else, right? I would have triggered right here and now like not up within this section where I'm printing it directly, right? So that's what would be going on there. And then I would go ahead and then pop off 1. I'd realize -1 is there. So then I'd go ahead and then print the -1, 1, right? Almost the same reasoning as the 2, 4. Then I go to 3. I'd realize 3 would would trigger this and trigger this, right? Because 3 does not have any children. So it would actually just error out when it says the node.left is not null, node.right is not null. So then I would just go ahead and print out 3. And then finally I print out 6. And this is when I account for the 5, 6, 10 case. And so when I'm doing the 5, 6, 10 case, notice that I would be going 5 first, then 6, right? Just like how we did previously. But then we would then go ahead and have 10 to be accounted for. And so then this 10, we have basically the same process, right? We just check the node.right is not null, node.right is red. And in this particular case, this tree would like not really have an issue, right? If I did something weird with like the check, right? Like I didn't sequence it correctly, because we don't have any more layers. So it's just sort of like the last node to be checked if -1 isn't. But yeah, like generally speaking, like if we had like more layers, right, that would be an issue that could pop up, right? But then we want to have 10. So that I believe should like match up exactly what we had before. So I'll just go ahead and like write in what we're doing, right? So we're checking node.right is not null. And then, oh, I have to do the 2 ampersands. Okay, right, so we have that. And then we're going to go ahead and print out the node.right.key. And then we're going to go and add in node.right.left, add in node.right.right. And then finally, if none of that works, we're going to add node.right. So a quick note is that this queue, right? Like I didn't even include, so let me actually write that as a quick note here. Doesn't include null elements, right? Because those would be skipped because of the if condition that we have in line 12. So just like the sake of like, I guess, ease. But that's sort of like how we think about this question, right? As at a very high level, what we're trying to do is we're trying to account for the fact that something is red. That's sort of the intuition that we were talking about way earlier when we weren't even looking at the code. And you want to account for that by sequencing it first, right? So we immediately print it out, right? You want to visit it beforehand within the same layer. And then what you're going to do is you're going to add in its children, right? That's why you have 2 lines for the queues. Otherwise, you'll just add it directly later, so it gets processed after it. Okay, well, I hope this was a fun question in terms of like, applying BFS to a red-black tree. But yeah, that wraps up this question.